Alright, in this video I'll be talking about how to derive the resolvent for a general cubic. So let's start off with the simple case, a depressed cubic, x cubed plus px plus q, and it is equal to 0. So we need to know the relationships of the roots with the coefficient of the polynomial. So if we use Vieta's formulas, we will see that the roots have a specific connection with the polynomial's coefficients. So the sum of the roots is equal to 0. And the reason it's equal to 0 is because our x squared term is missing. And the pair of the roots, the pairs, they relate to the x constant, so p. And all the roots multiplied is going to be negative q. And the fact that it's negative is because we have x minus u times x minus v times x minus w, where the constant would be negative u v w, which is going to be related to the constant term. That is why we divide by negative. So now what we will do is create a resolvent, pretty much a helper polynomial that will help us understand our cubic equation. And our resolvent will have a root or two roots using something similar to the sum of the roots, where we will have u plus v times omega plus w times omega squared. Now to find the next root, we just swap the square with the omega. So we have u plus v omega squared plus w omega. So the omega is simply just the root of unity. Negative 1 plus I root 3 over 2. This expression right here, y1 and y2 are not symmetric. So, in order to make it symmetric, we have to cube the expression. And the reason we want it to be symmetric is in case if we swap u, v, or w, the expression should remain the same. Like Vieta's formulas, they are all symmetric because if we swap u with w, none of the expressions will change. So, we're going to cube both y1 and y2. And normally we would have to expand the trinomial raised to the third for y1 and y2. But we're going to skip all of that algebra. And if we rewrite our quadratic in its factored form, we'll have y minus y1 cubed times y minus y2 cubed. And it is equal to 0. And here, we will simply expand, which gives us y squared minus the sum of the roots, y1 cubed plus y2 cubed, all multiplied by y, plus y1, y2 cubed. So, now that we have our expressions, we will go ahead and look for the y term, which is the sum of the roots of the quadratic, y1 and y2. So what we will notice is that if we have to expand everything, we get y1 cubed plus y2 cubed is equal to 2 times u cubed plus v cubed plus w cubed minus 3u squared v minus 3u squared w minus 3v squared u minus 3v squared w and minus 3u w squared minus 3vw squared plus 12u vw. We already noticed a few things. The 12 UVW. We have UVW, which is just negative Q. So we could rewrite this as negative 12Q. So we already have our first coefficient in our quadratic, which is negative 12Q. Now we need to figure out what is 2 times U cubed plus V cubed. So we will see that we have this, and we'll just look at the U cubed plus V cubed plus W cubed. And again, we would simply have to raise U plus V plus W equals 0 all to a third, which would give us this expression U cubed plus V cubed plus W cubed is equal to negative 3 times U squared V plus U squared W plus V squared W plus V squared U plus W squared U plus W squared V minus 6 UVW. And we could replace our UVW with negative Q, which will give us positive 6Q. The negative 3 multiplied by everything that's inside the parentheses nicely pans out to negative 3 times U plus V plus W times the pair of the roots, UV plus UW plus VW plus 9 UVW. And we see that our U plus V plus W is equal to 0, so our expression goes away. And we have plus 9 UVW, and we can swap that with negative Q, so we will get minus 9Q. And negative 9Q plus 6Q would give us negative 3Q. And since it's multiplied by 2, it will just simply be negative 6Q. And since we already looked at this portion as well, we could already just assume that we will have negative 9Q. Because this is also just what we had earlier. Negative 3 times the pair of the roots times the sum of the roots, which gives 0. And plus all of this, which becomes negative Q. So we have all Q's now. Now we could add everything, and we have 12 plus 9, that is 21, plus 6, that is 27, so we get negative 27Q. So we finally found out what that expression is, so we can rewrite it as negative, but it's positive now because the negatives cancel out, plus 27Qy. And now we simply have to go ahead and look at y1, y2. So if we just multiply our expressions, just the insides, we would get y1, y2 is equal to u squared plus v squared plus w squared plus u v omega squared plus vw omega squared plus u w omega squared plus uv omega plus uw omega. Finally, you have plus vw omega. This u squared plus v squared plus w squared is just going to give us negative 2p. And the right-hand side, u v omega squared plus vw omega squared plus uw omega squared will simply give us p omega squared plus p omega. We can factor out a p, so you get p times omega squared plus omega. Omega squared is equal to negative 1 minus I root 3 over 2. And omega is what we have here. So if we just add it all together, the i's will cancel out, and we will have negative 1 minus 1 all over 2, which is negative 1 minus 1, which is negative 2 over 2, which is negative 1. So we get that y1, y2 is equal to negative 3p. So finally, we could just switch all our y1 and y2s with negative 3p. And here we have our resolvent for the depressed cubic. And if we want to find the general resolvent for our cubic, we simply have to plug in p and q. For our general cubic, we have p is equal to c over a minus b squared over 3a squared. And q is equal to 2b cubed over 27 a cubed minus bc over 3a squared plus d over a. Plugging all of that in, you will get the resolvent y squared plus, and simply multiplying 27 times q, we will have 2b cubed over a cubed minus 9 bc over a squared plus 27 d over a, all multiplied by y. And plus, we will have b squared minus 3ac all over 3a squared all cubed. And since it is multiplied by 3, the denominator will just cancel with the 3. So we are simply going to be left with this. And a familiar form you might have seen in my previous video is here when we have a is equal to 1, which gives y squared plus 2b cubed minus 9bc plus 27d y plus b squared minus 3 cubed equals 0. And factoring out an a cubed from the expression of the y term, we have y squared plus 1 over a cubed times 2b cubed minus 9abc plus 27a squared dy. And factoring an a to the 6, we'll get, or 1 over a to the 6, we get 1 over a to the 6 times b squared minus 3ac. And multiplying by a to the 6, our general resolvent for a general cubic is going to be a to the 6 y squared plus a cubed times 2b cubed minus 9abc plus 27 a squared dy plus b squared minus 3ac cubed is equal to 0. So this is the Lagrange resolvent for a general cubic equation. So we have our general cubic ax cubed plus b x squared plus cx plus d is equal to 0, and its resolvent is simply this quadratic. So now that we have all that information for our cubic and the resolvent, we can finally just look for the roots independently now. If we also use 0 is equal to u plus v plus w. And if we just add all three equations, we will have u is equal to the cube root of y1 plus the cube root of y2 over 3. And if we're also including a, then we will have minus where the solution in general would simply be u is equal to a times the cube root of y1 plus a times the cube root of y2 minus b all over 3a. And solving for y in the quadratic resolvent, we will simply just get the answer for y1 and y2. And the other solutions are just easy to find. Just have v is equal to a times the cube root of y1 omega squared plus the cube root of y2 multiplied by a times omega over 3a minus b, and so on. To find w, you just follow the same process by eliminating everything else except w. And yeah, it's pretty much like a lot of algebraic manipulation to get the resolvent, but it's still going to give us the solution regardless. So hopefully you were able to understand where the Lagrange resolvent comes from and at least understand this vague explanation of the resolvent. So thank you, and I'll catch you on the next video.